All right, so your setup looked like this, where we had this sensor, and then here's the foot. So maybe that kind of gives you an idea of what was happening here. And this guy maybe rotated that way, and this one was rotating like this way, and I can't draw a really pretty picture, but I can sum some forces, and I can look at free body diagrams. Now, the hanging mass, the free body diagram, we've seen this one a million times, or maybe almost a million times, where there's a tension force up on it due to the string, but then there's a gravitational force on it due to the earth, the interaction with the earth. Now, which way did your mass go? Up or down? Down. So it's convenient to let the direction of motion be the positive direction. So when you sum these forces, they were unbalanced because there was an acceleration. We measured the angular acceleration of the spinning part of our system, but we could have measured the acceleration of the falling mass as well. We didn't, but we could. And we can actually come up with a relationship between those two. So the gravitational force is positive. The tension force is negative for my coordinate system, and that would equal m times a. So that was pretty easy, but that's not the only thing that had a force on it, right? We have this yo-yo thing that's spinning, so we can't just stop there and look at the acceleration. If I look at an overhead view, this was like the axle that we had the rope wrapped around, and you know the spinning, the rod would have been through here, so I'm just going to draw a shadow of the rod so you can kind of get the idea, right? That would be spinning. And then the cord was wrapped around and around and around and left tangent. So there would be a tension force on that axis, or the axle. So there's my axle. And that force was acting on the axle, but then it was causing it to rotate. So there's this force that starts causing this thing to spin. So let's look at how forces cause something to spin. And to do that, there's some lab equipment on your table right now, and we're going to set that up. So there's this radius here for your axle where you wrap the cord around, and in terms of twisting, you can have a force. There's a relationship between a force and the position of that force, and another force in the position of that force. And so the closer you are, the bigger that product will be. So when there's a small radius, like in this case, we get a bigger twisting than if we had used the bigger diameter on the three-step pulley. Because the bigger diameter on the three-step pulley would have been a bigger radius with the same tension on it. So take your same weight and move it out further. What happens? We get a bigger R, we get a bigger twisting. Yeah, what's up?
So if you have like the same mass on both sides, then how would you change the acceleration to like be able to compensate?
So this is torque. All right. So the torque is this twisting notion. So in equilibrium, the torque on one side is equivalent to the torque on the other side, and so they can be balanced. And torque itself is kind of like a force analogy to rotation. So like angular acceleration is analogous to linear acceleration. Angular speed is analogous to, so then your angular speed is analogous to the linear speed. Your linear position, like delta x, is analogous to your angular change in position, the delta theta. And so torque kind of gives us this analogy to how a force causes something to twist, thus causing it to accelerate. So torque, a net torque, causes, and I'm going to kind of leave this hanging for a minute here, it causes an acceleration, an angular acceleration. Just like a net force causes a mass to accelerate. So I wanted to come up with, like, what is this then? What is the mass analogy for rotation? Well, when a mass has a position with respect to the axis, then you can get, we saw that the acceleration changed. So your acceleration was much bigger when the radius was much smaller, right? So then the relationship between, if alpha is proportional to 1 over r squared, then that would be like alpha is proportional to torque, or alpha is proportional to 1 over r squared. So there's this r squared business in here. And if we had experimented with different masses, we all had the same little masses there, then this would be like the mass of the object. And so it turns out that our moment of inertia is what it's called, but the mass analogy is not just the mass, but it's the mass and its distribution. It's the mass and its position. And the fancy name for this is the moment of inertia. And the symbol we use is I, like a capital I, and it's the moment of inertia. So that's what I was wanting you to see, that there is this inverse relationship between the acceleration and the radius squared. The distance, the position of the masses. So as r got smaller and smaller, alpha got bigger and bigger. And then over here, with this force is applying a torque to our system. So the net torque on this axle would be the tension times the radius, and that is causing the whole system, the mass plus where it is. So that moment of inertia times alpha. And so this is what we were getting at. This is the new bit of dynamics that includes how something rolls, how the mass of the pulley is now a part of the problem. So when we had an Atwood system, and you probably are like, what is an Atwood system? But remember when we had the problems with the pulley, and then there was like a mass over here and a mass over there? All of those pulleys were massless pulleys, massless discs. Now we're going to put a mass on that pulley. So then now the tension on M1, this FT1 has to be different than this one because I have to have a net torque, which means I have to have a net difference in forces at those R's to cause the I, the moment of inertia of the whole disk, to alpha, to rotate, to angularly accelerate. Wow, big stuff, right?